Okay. Hi. Yep. I'm in the Alexandrova group. We're in the Chem department, electronic structure theory. We work with Wes, Eric, the Doyle group, Selivinsky group, and it's been a lot of fun. So I'm going to talk today about molecular design for optical cycling centers of larger molecules. Okay. Doesn't seem to work. Okay, so this is definitely preaching to the choir at this point, but essentially we're thinking of a cheap chemical screening tool that we can use to potentially find good optical cycling centers, good-ish, in that if they have decent Frank-Condon factors with a cheap level of theory, then we can start thinking about all those higher order important effects that Lan and previous speakers have been talking about later on to disentangle all these higher order vibronic couplings. But the whole point here is density functional theory is really cheap. We have an unpaired localized electron on our calcium, acts like a radical. That's very easy to treat with density functional theory. It's a pseudo-ionic bond, as Svetlana was talking about earlier, in that it resembles really an S to P-like transition. And then it was not really known if you could keep increasing this R group, because then that would require more repup lasers and seems kind of like a headache. But as Eric just talked about, you can just search the chemical space for organic ligands that have large homolumo gaps that are pretty far away from your calcium S to P transition and also strontium S to P transition. And that won't really interfere with your Frank-Condon factor at all because it'll be so far away that it won't disrupt your transition. And then, the reason why this electron withdrawing thing works when we add fluorines for this specific case is it makes the bond more ionic, as Eric talked about, and that makes your excited to ground state potential energy surfaces more symmetric. Okay, so Eric briefly talked about this, so I'll go through this a little quickly. But yeah, the whole idea is, can we extend these airing ring sizes maybe? We can't go all the way to graphene. There's no band gap there. That's a bunch of aromatic rings. Okay. I don't know the audience too well, but polycyclic aromatic hydrocarbons, there's a huge IR database. You can just search all these PAHs that can be made in experiment. And we can find, their homolumo band gaps, or homolumo gaps. And yeah, we find, you can go to coronene. It won't be perfect. So the blue lines are the homo to lumo gap of the rings, and then the black lines are like this S to P transition in calcium. And this is of the entire molecule energy. And so, yeah, we find we can go to coronene, and then ovalene will start to get flipping, and it'll start interacting with our calcium S to P transition. We can also go beyond aromatic species. So this is adamantane. It's really structurally rigid, which is really important, we're finding, for these kinds of good Frank-Condon factor species, and that we can also use attaching fluorines to this guy to increase our Frank-Condon factor slightly. It won't be as dramatic of an effect as when you attach fluorines to an aromatic species because electron withdrawing through resonance structures is a lot stronger than inductive withdrawing. But it can still improve the Frank-Condon factor a little bit, and then it can also, there's a limit, right? We just can't keep adding all these electron withdrawing species. We have to think about the next order of like vibrational modes, vibronic coupling, things that could come into play. So for example, the far right fully substituted fluorine for CaO adamantane has a lower Frank-Condon factor than like 5 fluorines on this adamantane. And that's because it goes from a symmetric stretch being the main off-diagonal decay to actually a bending mode. And we kind of design all of these molecules to have just very vertical stretch-like transitions, so we want to favor the stretch as our main off-diagonal. We can take this theory, so adamantane in a surface kind of looks like diamond, and diamond's very structurally rigid as well, which is why this works. It has a band gap. Well, it could work in theory. And the electron remains localized on our calcium here. It's actually kind of hard to predict Frank-Condon factors in solid state because of periodic boundary conditions. You'll need a super large unit cell. It's hard to calculate excited states, but we actually have a lab mate who's working on this with an embedding technique, so to embed defects into surfaces. So Maybe we'll get an answer soon. He's collaborating with MolPro, so that should be available soon when he finishes that up. But the same rule applies, right? As long as the band gap is not near the calcium S to P transition, it should, in theory, remain localized. And then people have started proposing, multiple optical cycling centers. This could be interesting in terms of super radiance effects. If you can align your dipoles, like in J aggregates and chromophores. Again, not sure how relatable that is to this audience, but it could be pretty interesting. You'll get like subradiant states, super radiant states. Figuring out how to tune these super radiant states to be lower in energy than the subradiant states is interesting. But also an issue, right, is that they're degenerate. It'd be nice if we can individually address these. So one way is you could just use different metals, right? Calcium and strontium are far enough away in energy that you can kind of individually address these by just changing the metal from calcium, calcium to strontium, calcium. And the phenyl group is far away from both of these. Also, you could start thinking about symmetry, breaking symmetry a little more, as people have talked about earlier. So this is adamantane. It's C3V symmetry, but when you add another optical cycling center, that breaks the symmetry a little bit, slightly perturbs the states. But you can see the excited states still have some density on that other calcium atom. So what you can do is you can just add a substituent to further break these so that they're sufficiently far apart so that you can individually address these atoms. Okay, so now, not the most elegant transition, but I wanted to talk about a little work that we've done with Debayan recently, who talked about calcium hydrides. So the case on the left that I talked about optical cycling centers is that there's a huge need for just searching the chemical space in a smart way. Maybe DFT could be the answer for cheap screening, and we mainly focus on radiative transitions. And then calcium hydride was a really fun project because it's a diatomic. We really think it's non-radiative transitions that are important for predissociation. And we need the full potential energy landscape, so we need high-level MRCI and relativistic effects. So the story here, Ian and Debayan really set a great stage for that this morning. There's like 4 adiabatic potential energy surfaces that we really care about. So Debayan and the Zelevinsky group are trying to create ultra-cold hydrogen from fragmentation. And a really common loss pathway is this pre-dissociation. You can kind of see this A2 pi state and this B2 sigma plus states are pretty close to the ground state dissociation energy level. So they were worried that some kind of pre-dissociation loss could be had there. And working with Lan, he just estimated cheaply some spin orbit matrix elements and found that the interaction between the A2 pi state and the B2 sigma plus state will be relatively small. So for now, I just included 3 states in my model, but I can go back and add A2 pi and also spin orbit coupling with that. So we can definitely afford it because it's a diatomic molecule. So the whole idea here is there's some vibrational states. There's also higher vibrational states in this B sigma plus state where the wave function is no longer localized in the first well. Around like V equals 4, it starts localizing on the second minimum of this B sigma plus well. And that could be pretty interesting because you can kind of see the non-adiabatic coupling of your surfaces increases at that point. So the main questions is how can we model non-adiabatic coupling accurately, and how can we model transitions to the ground state continuum? So brief tutorial on MRCI. So there's full CI, which you basically have a basis set of your orbitals. It could be a single particle basis. Chemists, we use the Hartree-Fock expanded basis set with excited determinants, as Pavel kind of gave a preview to with couple cluster. And then the whole idea with MRCI, it's just a truncated active space because we can't afford full CI for calcium hydride. There's too many electrons. But what we can do is we can choose important electrons and orbitals that we think are important to create our potential energy surfaces, optimize these orbitals within this active space, and then run a full CI of variationally solving these coefficients. So then we could use some utilities and electronic structure packages, but They're designed for molecules, which have more vibrational modes. They'll use a harmonic approximation. We want accurate Frank-Condon factors. It's cheap enough. I just decided to put this on a grid in Fortran. So we can use our MRCI energies and fit it to an n polynomial spline interpolation. It's already a built-in fitting in Fortran. I use a Colbert-Miller real space representation of our momentum operator. This is actually nice. I think LAN uses it in a previous model too, which is kind of fun. But it converges way faster with larger grid size than like a 5-point stencil and finite difference methods. And we need to keep this momentum operator in real space because we're going to use this Hamiltonian where this Aij is this non-adiabatic coupling. So the output from MRCI is in real space. So it just felt easiest to me to keep the momentum operator in real space. And then you can just add this in your Hamiltonian. And then when I do that, Debayan already talked about this, so I won't spend too much time on it. We get pretty decent Frank-Condon factors. I think there's still a ton of room for improvement for these potential energy surfaces. Talking with some people here has been really helpful in terms of different fitting procedures, including experimental vibrational spacings and fittings and things like that. So it's been a really great conference for me. So then we have to mimic the continuum. So you could definitely afford a couple of channels approach here, and I'm not saying you shouldn't do that, but I've already built up this Hamiltonian in Fortran. It's seemed easy to just use some scattering. What people did in the 1990s was essentially they'll add a short-range optical absorber to their potential. So like the ground state is what I want to model as a continuum. You can add like this imaginary optical absorber at the asymptote or whatever dissociation energy level you have. From there, what this does is it imposes essentially a boundary condition on this wave function. It absorbs like the outgoing wave, so it's just kind of like a 1D channel flux equation. And Danny Neuhauser, he's an electronic structure and also a pseudo-theoretical physicist. He did a lot. It's like the line's kind of blurred, I guess, in the 90s there. But he did a lot of this and compared his optical absorber method with a couple of channel scattering calculations and actually found pretty good agreement in transition amplitudes for like collinear reactions. So I lucked out because Danny's down the hall from me. So I went and bothered him about some papers he wrote 20, 30 years ago. And he helped me out with placing this optical absorber. So our matrix values are no longer Hermitian because now we have this imaginary absorber in our ground state potential. And it turns out that the excited state imaginary eigenvalues are just these transition probabilities to our continuum because it's just absorbing this outgoing wave. But if you want to sanity check this, you can take an uncoupled excited state like that B plus sigma state, no non-adiabatic coupling, no other states. And then you can take our full Hamiltonian, where I have the optical absorber in the ground state, and it's fully diagonalized with 3 states. You can get psi of t. Don't propagate in time, right? We already have this diagonalization already, just saves you time. So we can get psi of t just from this diagonalization. We can get our transition probability in time, and we find that it decays as in decaying exponential. So then we can just fit gamma to this, and we find that the gamma agrees with our negative, our imaginary eigenvalue. And from there, 1 over gamma is your time constant. And then we had to relate it back to Debayan's measurements because it was hard for them to get, obviously, time-resolved time constants to compare to us. So we just decided to come up with this ratio of our lifetime to the radiative lifetime of the B state as some sort of pseudo-probability. And we find that our measurements agree pretty well, which is kind of surprising considering we haven't added spin orbit coupling, we haven't added fits with experimental data and all this stuff. I expected results to be a little more sensitive to this. And once we have this, I think I need to go back and add spin orbit coupling for the pi to sigma plus state. But then we want to check higher vibrational B states, predominantly where the B is localized on that second minima. And then we also have already our wave functions, so we can also just predict spontaneous emission as well. And once again, Ian had some great suggestions for software for fitting with experimental data. So I guess I'll end with that. We've had a ton of collaboration with a lot of people at UCLA, the Doyle group and the Zelevinsky group. So thanks.
It's pretty inspiring to see all those molecules, and the basic idea, right, is this alkaline earth metal pseudofluoride kind of bonding.
Yeah.
Right? And I'm just wondering, it hits me that we make these molecules actually at low temperature. We have these buffer gas cells that are like at 4 Kelvin. You can imagine, and I want to know if you've thought about this or what you think, whether it's possible to have some kind of van der Waals bonded optical cycling center. So here the bonds are pretty strong, right? They're, you know, EV-ish.
Mm-hmm.
Is there something that we could optically cycle, but that was van der Waals bonded to a molecule? So you, just like an example, you can take like ethanol. You could take ethanol and have something van der Waals bonded to ethanol and then optically cycle that, or will it just kind of pop off, do you think?
I think it really depends on the internal energy level structure to say. Yeah, people are thinking about even more like Rydberg-like orbitals in these molecules as well. So I'm not sure. Sorry, I can't give a better answer.
So just think like that surface, that was, you look at that surface, you can imagine decorating it with something that just barely sticks, but it's not like, it's not a covalent bond, it's not an ionic bond, it's just like there with a, say, 100 Kelvin binding. And we usually don't think about those because they don't exist like at room temperature. But since we're making molecules at 4 Kelvin anyways, you can imagine those kinds of molecules. So an experiment, sorry to monologue here, an experiment we did, I forgot, 15 years ago, we made silver helium molecules.
Oh, very cool.
Yeah.
Yeah.
Because we were low enough
Silver is
temperature.
hard to model with a solid state, but we could, yeah, we could think about that. Yeah, that's actually very interesting. Huh.
Yeah, so for these, multiple cycling center experiments, have you thought about anything other than an alkaline earth? For example, Danny and Stefan talk about aluminum chloride. Could you imagine aluminum on one of these, and then you can have maybe some like alkaline-like transitions on one of your 2 cycling centers?
Yeah, I think it's possible as long as you can keep. So the reason why we're choosing these optical, like alkaline earth, is that they're 2 unpaired spin, pretty spatially separated. It's easy to chemically screen with a cheap, like DFT. Yeah, you can think about having a vast array of different kinds of molecules that have this unpaired spin as well. You can also think of, like, obviously superacids could be kind of interesting too. Yes.
What about an atom inside of Buckminster fullerene?
Yeah, like a superatom, or
Just a sodium atom.
sure.
It would not. I mean, Buckminster fullerene is a terrible trap for density of state, but if you're not talking to it, it's a molecule.
I would have to check the fullerene band gap to make sure it's, or homolumo gap to make sure it's far away. I think the homolumo gap of, so also it's not clear to me whether, so people have proposed this, as Svetlana has talked about. It's not clear to me like how these breathing modes of the CH will start affecting the Frank-Condon factors at a high level, kind of what we talked about with the CH and calcium phenoxide with vibronic coupling. So we're not sure, but that could be an interesting direction.
I have a question related to that. So kind of, if I take a benzene ring and I replace all of the external hydrogens with cycling centers, so
So we tried this at first. Okay, so yeah, I'm working on actually. So it's not a horrible question. I'm working on a larger ring. So then you're thinking of super radiance in a ring.
Yeah.
Yeah.
To zero order, do I get like 6 times better photon scattering rates? Or
Yeah. So we're thinking about that. You have to keep it sufficiently separated. So there's a nice distance before they just want to like start bonding with each other, or bending essentially. Like bent conformations are more preferable if they're too close together.
So you're imagining taking every second, for example?
Yeah, something like that. You can go back to the polycyclic aromatic hydrocarbons, or even these like 3D space guys. Yeah.